In this video, we're going to explore how we can determine the formula of an unknown hydrocarbon by a combustion reaction. If we have an unknown hydrocarbon containing carbon and hydrogen, we can combust that, in other words, burn it with an excess amount of oxygen, and when all of the sample is used up, we will have been able to collect water and carbon dioxide, which are the only products of this type of reaction. Doing so will then allow us to go through several stoichiometric calculations in order to determine how much carbon and hydrogen had to have been present in the initial compound. Earlier in the semester, we were looking at empirical formulas, and the question came up of why empirical formulas were useful. This type of combustion analysis shows us exactly why they are useful. What we can do is take an unknown hydrocarbon, combust that, and then use our amounts of carbon dioxide and water collected in order to then find the empirical formula of the compound, which is what we're going to do in this example. Here we have a certain unknown hydrocarbon, which consists of carbon, hydrogen, and oxygen, and we're going to use our results of the reaction in order to determine the empirical formula of the compound. We might also have some mass spectrometry data available, which will tell us the molecular weight of the compound, enabling us then to find the full molecular formula. So let's see how we go about this. When we look at the equation for the combustion of an unknown hydrocarbon, we can see that the only products are carbon dioxide and water. And so, if we're able to know how many moles of carbon we collect in the carbon dioxide, we see that the only source of that was from our initial unknown. And so the number of moles of carbon in the carbon dioxide has to be equal to the number of moles of carbon that we initially had in the unknown. Likewise, if we can find the number of moles of hydrogen that we collect in water, that had to have been equal to the number of moles of hydrogen originally present in our sample. It's a little bit different looking at oxygen, and so we'll take a look at how we do that later. First, though, what we want to find is the number of moles of carbon and hydrogen that are present in our products. And so we said that we collected 2.082 grams of carbon dioxide, and so our first step is to convert that to moles of carbon dioxide. We know that every 1 mole of carbon dioxide contains 1 mole of carbon. Therefore, there had to have been 0.04731 moles of carbon present in our initial sample. We then do the same thing for hydrogen. We collected 1.705 grams of water. We use the molecular weight of water to convert that over to moles of H2O. Then we do have to recognize that there are 2 moles of hydrogen for every 1 mole of H2O. And so don't forget that ratio. And so we calculate that we had to have had 0.1892 moles of hydrogen present in our initial sample. So now we know how many moles of carbon we had to start with and how many moles of hydrogen we had to start with. We've got to think about oxygen at this point. We're not able to determine the oxygen directly from the carbon dioxide or the H2O. We have to think about what's going on in this reaction. We're taking our unknown hydrocarbon and reacting that together with an excess amount of oxygen. And so we don't know how much of the oxygen in the CO2 or the H2O might have come from the excess amount of oxygen present initially or from the hydrocarbon. So we have to go about oxygen a little bit more indirectly. We do know that the only things present in our sample were carbon, hydrogen, and oxygen. Therefore, if we can take the initial mass of our sample and subtract out our mass of carbon and hydrogen, that will tell us how much oxygen had to be present initially. And so we calculated earlier that we started with 0.04731 moles of carbon. We convert that to grams using our molar mass. And so our initial sample had to contain 0.5682 grams of carbon. Likewise, we found that our initial sample contained 0.1892 moles of hydrogen. We convert that over to grams using our molar mass. And we find that our initial sample contained 0.1907 grams of hydrogen. And so we can then input those and subtract them from our total initial mass. And we find a mass of oxygen of 0.757 grams present in our initial sample. We can then do what we did before and convert that over to moles using our molecular mass. And so we find that our initial sample had to contain 0.0473 moles of oxygen. We now know how many moles there were of each element in our initial sample. And so, just like we've done before when looking at an empirical formula, we know all the number of initial moles, and so we will take each of these and divide them by the lowest number. And in doing so, we find that our subscript on carbon has to be 1. Our subscript on hydrogen will be a 4. And our subscript on oxygen will also be a 1 for an empirical formula of CH4O. We also want to find the molecular formula of this compound. And so to do that, as we've discussed before, we're going to take our molar mass that we were given and divide it by the empirical formula mass. And so we find the empirical formula mass by simply finding our molar mass of CH4O, which we calculate to be 32.04 grams per mole. And we divide our molar mass that we were given by that empirical formula mass to get a factor of 5. In other words, our actual compound is 5 times larger than what our empirical formula was. And so we need to multiply all the subscripts in our empirical formula by 5. Our empirical formula was CH4O. Therefore, our molecular formula is C5H20O5. Let's take a look at another example. Here we have an unknown biochemical substance which contains only carbon, hydrogen, and oxygen, and we burn that with excess oxygen. We analyze our results, and we find that we have 18.942 grams of carbon dioxide and 7.749 grams of water. We're also able to find the molecular mass of the entire compound at 150.13 grams per mole. And so using this information, we're going to calculate our empirical and molecular formulas. And so let's remind ourselves of what our general chemical formula is. We have our unknown hydrocarbon reacting with oxygen in order to give us carbon dioxide and water as our products. The first thing we're going to do is use our amounts of CO2 and H2O in order to calculate how many moles of carbon and how many moles of hydrogen were initially present. And so we calculate those through, and we find that we had 0.430 moles of carbon and 0.860 moles of hydrogen initially present. Now we want to find out how many moles of oxygen we had. And so remember, in order to do that, we need the mass of our initial sample minus our mass of carbon and our mass of hydrogen that were initially present. And so we know that we started with 0.430 moles of carbon. We convert that to grams. For 5.164 grams of carbon. We started with 0.860 moles of hydrogen. Convert that to grams. For a total of 0.867 grams of hydrogen. We can now use those numbers to find our mass of oxygen. We simply put them in for our mass of carbon and hydrogen up here. And so minus 5.164 grams of carbon, minus 0.867 grams of hydrogen, gives us a total amount of oxygen of 6.884 grams of oxygen. Next, we want to take those grams of oxygen and convert that over to moles. And so our 6.884 grams of oxygen divided by our molar mass of oxygen gives us 0.430 moles of oxygen. We now have all of the information we're going to need to find our empirical formula. We know how many moles of each element we initially had present. And so, as we've done before with empirical formulas, we can take each of these and divide them by the smallest number in order to find our subscripts. And when we do so, we find that our subscript for carbon is 1, hydrogen is 2, and oxygen is 1, for an empirical formula of CH2O. We also want to find our molecular formula, though. So to find our molecular formula, we're going to calculate the mass of our empirical formula. So just like we've calculated molecular mass before, for an empirical mass of 30.025. We then take our molar mass of 150.13, divide that by our empirical mass, and we get 5, which tells us that we want to take our empirical formula, scale that up by a factor of 5 in order to get our molecular formula for a final molecular formula of C5H10O5. And so in doing so, we've taken a completely unknown compound, we were able to send it through a combustion analysis, analyze our products, and get a final determination of what the actual molecular formula is of this unknown. This is used quite often in order to find the identity, or at least the formula, of an unknown compound. Combustion analysis is a powerful analytical tool. I hope you found this video useful. If you want to find some more practice and more information, there's plenty on the website.